Hi everyone, this afternoon we will discuss another application of our differential equations, which is entitled growth and decay. It states that when the rate of change of the amount of a substance or a population is proportional to the amount present at any given time, we say that this substance or population is going through either a decay or a growth, depending on the sign of the constant of proportionality. Right, there are times, class, when, for instance, a population grows, or the population or the amount of a substance decays, and many such times, the, the rate of growth or the rate of decay is directly proportional to the amount present, the amount of the substance present at any given time. So, for example, if there is a smaller amount present uh, at any given time, let's say at t equals 1, then for instance, if uh, one substance or one organism uh, at t equals 1 multiplies to 2 or produces another 2, so the 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 more substance you start with, the greater the amount of substance you end up with at t equals, let's say, at t equals for any given time t. All right, so here you have 2 to start with, and here you have 4, and we know that the rate of growth of this substance is directly proportional to the amount of the substance present at any given time, in which case the amount of substance here is 2, whereas the amount of substance here is 4. And so it grows exponentially depending on the amount of substance it begins with, right? So that is the law of growth and decay. So the derivation class of the formula is much the same as the in principle as the Newton's law of cooling. For instance, we have A as the amount of substance present at any given time, amount of substance present, okay, amount of substance present, and we have T as the time, okay, time, and we have K as the proportionality constant, okay, proportionality constant. Then the differential equation we have is dA over dt, which is the rate of change of the substance, is directly proportional to KDA, which is where K is the proportionality constant, and I'm sorry, KA, KA. All right. The rate of the change of substance A is directly proportional to the amount of the substance A to start with. Okay, so this is the differential equation we will be using to derive the formula for growth and decay. Just the same with Newton's law of cooling, we do not have to place a sign here, positive for growth or negative for decay, in K, because it will later on, it will just later on have a positive or negative sign depending on the givens, depending on the problem. Okay, so for me, although in some books and other resources, they always give a positive sign for K when it comes to growth, but negative for decay. But at times, you may have a problem whether you are dealing with a growth or a decay. So my suggestion is you do not have to place a sign in K, and it will just come out whether when it is growth, it will just come out positive. When it is decay, when you are dealing with a decay problem, it will just come out as negative. Okay, so it depends actually on your given. Okay, so let me erase this first. Okay, And then we will start with our derivation for the law of growth and decay. So we start with dA over dt, the rate of change of a substance, is directly proportional to the amount of substance present. Then we have dA over A equals dt. Okay, we use again what we call separation of variables, which you are very familiar with already. And then we integrate. So we have here ln of A, and here we have k, so this is k dt, so we have integral of dt is kt plus ln of c. So instead of just writing c, we write ln of c. Then we transfer ln of c to the left side in order to group like terms. So we have ln of a minus ln of c. Then we have ln of a over c equals kt. Here we have kt, which is the term on the right side. So and we raise everything to e. So we raise everything to a in order to take out ln, so that is e to the ln of a over c equals e to the kt. Alright, then what is left on the left side is a over c, and on the right side we have e to the kt. And then transpose c to the other side, we have c e to the power of kt. So this is the equation we will use for problems relating to growth and decay. A equals c e to the kt, where a is the amount of substance at any given time t, k is the proportionality constant, t is the time, and c of course is a constant which we will be deriving in when we derive the particular equation. So this is the general equation, a general solution I mean, and our task is to first find c, the arbitrary constants, and the k. So once again, you do not have to memorize the formula because the problems sometimes vary. So if you memorize the formula, you will not be able to know how to derive the equation if there are slight changes in the problem. For instance, how about if the question being asked is find the amount of substance present at time equals, let's say, 5 minutes. If the rate of change of the substance follows the model where the rate of change of the substance is directly proportional to the square of the substance present, square of the substance initially present. So you cannot anymore use this equation because you have to start with the equation, with the differential equation, dA over dt equals ka squared, because the rate of change of the substance according to that particular question is directly proportional to the square of the substance present at initially present. So but if you know how to derive, then when asked with that particular question, you can simply write it first in terms of a differential equation, this one, and then you can separate the variables, and then you can derive the formula and solve the problem. Okay, so in the next video, we will be tackling some problems relating to growth and decay of a population or of a substance.